All right, welcome everybody. Thanks so much for coming to this tutorial for KaiPy at the GEM 2024 meeting. I am Mike Wilperger. I am one of the members of the Center for Geospace Storms, which has been developing this KaiPy package as a tool for helping us and we hope you to be able to analyze, visualize, and just generally play around with the output of the data that comes from the MAGE model that's being developed by the center. Joining me today in the room to try and help out are Adam Michael. Adam, wave your hand, and Anthony Sigola. They're two of our great folk scientists on the team, and they'll be here to kind of help mingle around and answer questions for things as we get into the more hands-on online portion of this tutorial today. The last person I formally wanted to introduce is Eric Winter. Eric is a software engineer / recently minted space physics PhD. Congrats, Eric! And he's been making sure that the spaghetti challenging code that we scientists write is turned into something that's a little bit easier for other folks to be able to utilize and do with that. And then the last thing I do need to do, I would be a long list, is to acknowledge all of the folks on the CGS team: Kareem, Kevin, Dong, Anthony, Adam. I'm going to blank on all the names. People that contributed code to this code base. You're going to be using and seeing some stuff that the numerous members of our team have made possible, and it wouldn't be here. I wouldn't be able to stand up here without the great work that those folks have done to be able to do that. All right. So with that, the way we're going to break this down is I've got a few slides, do a little bit of background, give you a little bit of scope, and then I've got some stuff that we've set up on some Google Colab notebooks to be able to let people do a hands-on experience, and we'll go through that. There'll be some stuff where I click on a couple of things, and then we'll go off and give you a task to do, and we'll mingle around to try and be able to do that so that you can get at and understand how to use the MAGE model output that comes into play. I tried to think about what to do in this session, and I'm focusing here on trying to teach you guys what some of the basic tools and basic capabilities are for being able to analyze and look at the results. I decided not to pursue the pathway of having everybody install it and getting everything working there, because Python environments are just crazy and getting everything to go. It should be as simple as a pip install. I'll get to that later on, but it usually isn't. So we're not going to do that here today. But that said, if you run into problems when you're back home and whatnot, you can always reach out and email me, and I'll be more than happy to help you go through that process and get going on it from there. So that's just a little bit of scope of what we're doing with the thing itself. The other key point that I should make here is that we are not talking about how to build and compile and run the MAGE model itself. The main modality that I see for folks being able to do stuff on their own is doing runs through our colleagues at the CCMC. I'll come back and touch on this a little bit later on, but they have an option for you to be able to download the results from that, and you can use all of these tools with the results that are coming out of runs at CCMC for that itself. For those of you that really want to get in there and get dirty and hands-on with the model itself, stay tuned to this space. We're hoping and planning for our first open source release of the MAGE model in the fall, around our annual meeting, AGU kind of timeframe. And I suspect that I'll be back here next year at GEM doing extension of this Python tutorial and more about being able for folks to be able to run and do stuff with the model itself. So just a little heads up on what we're planning to do in the space today. Okay, so for those of you that don't know, MAGE is a model that MAGE is an acronym, and it stands for the model, multi-scale atmosphere geospace environment model. It's available for runs on request right now at CCMC, and the version of the model that's available at CCMC is what we're calling MAGE 0.75, and it has three components. It has the Gamera magnetosphere component, so that's the MHD solver for the magnetospheric portion of the domain. In the inner magnetosphere, we're using the Rice convection model to do the inner magnetosphere model, and then those things are coupled to a high latitude ionospheric electrodynamic solver to solve the cross polar cap potential and those patterns. That's called Remix. If you go to the CCMC webpage and do a search on MAGE, or go to their model catalog, you'll be presented with this page, modulo the little inset movie that I stole from one of the summary things and stuck on there in there, but it should just look like that. And if you want to do a runs on request, you can do that there. The instructions are pretty straightforward for that process. But this is the component and the version of the model that the KaipyTutorial will be focusing on. Here it is today. I did just briefly want to touch on what can you do with this when you get home for being able to install it. KaiPy is our Python package for analysis and running. It is on the Python package index, so it's pip installable at the moment. Right now, we want to work on Python versions between 3.8 and 3.10, and that's primarily going higher than 3.10. There's some library dependency issues that come into play. 3.10 is pretty stable. I think that's what you end up seeing at a lot of places. So we're able to do that. You should be able to create your Python 3.10 or 3.8 environment, do pip install KaiPy, and it should install all the dependencies. You should be good to go with it from there. You can scan the QR code on the page, or just go to pypy.org and search KaiPy to get to the installation for it from that side of things. We, the team, have been working really hard to create documentation for you to be able to do that. And we've decided on using the Read the Docs platform for doing the documentation. So we're going to go overview. I'm going to provide you some introduction to stuff, but every function, every script that we have as part of the KaiPy package has a doc string, and that's been compiled and brought into our Read the Docs page there. The QR code works, or KaiPy-docs at readthedocs.io. So it's on the open source version of it there, and it should be pretty good. The one thing that's there that I'm not planning to spend a lot of time on covering today, but we do have made available, is a whole bunch of scripts that sort of automate the process for being able to look at these things. For making movies, for example, quick look movies, and making some summary time series plots. Those are all distributed as part of the package. They're in a scripts directory that comes with your pip install, and the vast majority of them are documented. Building documentation is almost a lot like building a code these days, right? You got to get it all in there. You got to get it in the right format. Then you got to run this make process. Then you got to go get it on KaiPy, and then got to build a container and then do the installation in there. So it took me a long time to get all that worked out. So I didn't make it through all of the scripts that we have. So the documentation will be being updated and evolved as this goes along. But I did emphasize looking at the quick look directory in the scripts thing that has a bunch of these plots that I think and analyses that you might like to look at for doing summaries. For example, making a movie of the ionosphere, or making a movie of the magnetosphere. There are functions in there to handle doing time series plots. And you can learn a lot more about those by going right to the documentation and then clicking on the KaiPy scripts, and then scrolling through and finding the ones that you want from there. So that documentation exists. All right. So now here comes the scary part. Let's jump into trying to make this actually a hands-on interactive tutorial for what we're wanting to do. So I've made a notebook that is available on Google Colab. You can scan the QR code, but probably your laptop's not going to let you do that. So I also made it a bit.ly link. So if you do bit.ly/mage, a capital MAGE tutorial, capital T tutorial, you should end up on that page, and it should come up for you to do that. So I'm going to hold here, let people try to get there and get things going. Let me know if you have problems getting to that point, and then I'll send my minions out to try and help you. So you should be able to, once you get there, you can just we can start running and doing that. You might, if you have a Google account, you might want to make your own copy of the notebook, so you can save it for yourself, and you can and make changes and do other things with it on your own to save it there. Is everybody there? Anybody not there? Let me phrase it that way. All right, I'm gonna stop showing this screen and switch over to the other screen. So we can go through the tutorial portion of this. Stop share. All right. So now I got to share my screen over here. Okay. So, whoop. Why did it not? Oh, fascinating. Okay. Let me. Um, I've done Zoom. Let me see if I can make this be the Zoom screen. So if I move this over to there, yes. But why is this not? There we go. Yeah. Can I pin that? I guess that's probably. I go what? Full screen. There we go. That's better. Okay. Sorry. Takes me a moment to figure out how to get that to go. So everybody should be seeing a screen like this that is the a standard Jupyter notebook for the interaction for things today. The notebook, if we open up the little thing on the side here, you can see that I've kind of got it into some generic things that we're going to do. The first thing is going to be setting up the Google Drive to do two important things. One is to get the Python package on there, and two is to be able to get you guys access to some simulation results. And so for the first portion of that, I've taken a small sample, a small slice from some simulation results, put them on my Google Drive, and then I'm sharing that Google Drive out. So we got to get Colab to be able to talk to and see your Google Drive. So you should be able to click on the link that's in here and follow the steps that are being shown in this graphic here. So if you click on that, it's going to open up that directory. Then click on the directory name, go down to organize, and click add shortcut. And then this will add it to your drive as a shortcut that's accessible to the Google Colab portion of things there. So this will not be taking up any space on your Google Drive. It's just a link to where I have it and whatnot on the Google Drive. All right. Everybody having success on that? Anybody not getting that to work? It will, well, actually, a little later on, it's going to ask you for permission. We'll come back to that in a second here. All right, I'm gonna click through the next couple of things, and then we're gonna pause after we get through the next stage to make sure everything's working for folks there. So we're gonna run the next cell, which is just importing the Google Colab thing. And this is what I do want to have people see is that it's going to ask for permission to connect to your Google Drive to be able to see things to come into play. And you do need to grant permission for it to be able to get on there to continue to do what we're being able to do at this point in time. So run those little things, grant the permission, and it should pop up with it going through for that part of the process. So mine succeeded, taking a whopping 23 seconds to be able to do it. And then the next part is installing the Python package. And so we'll click on that. This is where it's using the fact that I've got that symlink going for being able to get to the thing, and then it's downloading and doing all the fun little install. For me, since I've already run this, it's got it cached. But some of you, it may take a little bit longer time to download for it from there. I am going to stop there. Oops, I'm running the wrong one. Ah, crap. That's okay. We'll just it's the same basic steps here at the beginning. Grant permission. All right. So now returning to where I was before with the installation. It's just installing what it needs to install to get things to be able to do that. If you were doing this on your machine at home or your environment, you would one time need to do the pip install the package, and then it would become available to you. You don't have to repeat this every time, but. So you probably didn't do the shortcut setup correctly. When Adam finishes with lots, he'll come over and help you out. Did you guys? Are you guys good over there? Did you guys get in? Okay, maybe. And you're good in the back. Are you good? Cool. And then looks like a couple more folks there. All right, so. Okay. All right. So let's try this. All right. So some folks are running into what appears to be a lag problem here. So I guess what I'm gonna suggest we try to do is a temporary workaround here is in the background on your Google Drive. Try downloading the things. It's not that big, and then we can push it up manually to a folder and change the paths and get people going on that to do that. So while folks are trying to do that, and I guess somebody else was saying that if they just waited a few minutes, the lag resolved and it showed up on Google. So um, shame on me for trying to think that it was going to be straightforward for the data to get there. So apologies on that front. I'm gonna keep going with a little bit of the tutorial side of things for the notebook, and then we'll be mingling around here for folks to get everybody going forward on that front. So once Google gets things mounted and you're able to see things and the data comes across, the next step is to do fairly standard Python things that come into play. First, we're going to import some modules that are fairly standard Python modules for plotting, and that's the matplot library and the NumPy package that comes into play. So when we do that, those get imported there. And then we're going to import several packages that come as part of the KaipyTutorial package for being able to do that. So the first module that we're importing is the KaiViz portion of the Python package here that has our routines for making plots and doing that. And then the next three modules that are being imported are the modules that we handle for being able to read and import the data. The MSphere, the MSphere Viz also supports doing Magnetosphere visualization stuff, and then Remix and MagSphere are the pipes, the pathways for getting the data out of the HDF files that we create down into the Python NumPy arrays to be able to do that. So if I do the import on that, we're going through and things are getting imported and happening here, and we got that going. So, okay, how many people out there do not have the data on their machines yet, are not able to go forward on this? So I got 1, 2. Okay. All right. We'll have Adam and Anthony will try and help those folks out with that as we go along here. If you could, Adam, help her to just download the entire gross REU directory, and then we can just upload it, and that should put it onto her drive, and we can get around it that way and just put it in some different directory and work around the path issues for that. Okay. Moving on to the next step here, and that is actually getting into being able to visualize the data and looking at it there. So we're going to look at visualizing some stuff for the magnetosphere. And the first step in that process is being able to set up the pathway between the HDF5 files that are the output of the simulation and the simulation results. And so I'm going to actually using some results from a fairly simple simulation that I set up to run to help Nick Gross onboard some students that are working on a research experience for undergraduates at CU. So we need to tell the code where the files are located, and the way we have our naming convention set up for the files is we give everything a little base name, and a name at the begins at everything that lets you know where it is. And so they're in the the base directory and this gross RU thing, and then this gross RU slim. The slim actually corresponds to the fact that I trimmed it down to just being 2 time steps that are available in the run there. And then the next step is to be able to actually get the data imported. And so the GAMsphere object is the pipe that's going to get us into the thing that actually grabs the data and gets that going into it from there. And so this is going to give us some information telling us about what it's doing. It's looking first for a serial output file, not finding that, then looking for MPI. It's finding it in the MPI version. There are 2 time steps in this file. It's a 96 by 96 by 128 grid. It's got magnetic field, plasma variables, velocity variables that are in there. It has modified Julian date for the way we keep track stuff, and the remix data. So how many folks have been able to get to this point and read in the data and see the initialization? 1, 2, 3. Okay, so we're about 50-50, so I'm not doing so great on my capabilities here, but we're getting closer. We'll be around to help folks get through the rest of it that comes into play there. The general way that we play around and access stuff is by accessing it by the step that it was the output from the simulation here. There is an object within the pipe that is all of the steps that are available. There's also the start step and the end step, because those are useful things if you want to loop over things to have access to. And so right now I'm just going to grab the last step that's in the file and set that equal to this end step variable. And have that happen. So I got the step that I'm going to be able to go ahead and grab. All right. Continuing on, let's make a plot. So to make a plot, we're going to use various components of the KaipyTutorial package and underlying standard sort of matplotlib tricks that are out there. We're going to pick the domain that we want to look at here. So we're going to set up the boundaries for it, and in this just a simple list here, the xmin, the xmax, the ymin, and the ymax. So I'm going to go about 20 RE upstream, about 100 RE down the tail, plus or minus 60 in the y direction to be able. Actually, I guess it's actually z for this plot that I'm going to show first, but it's z and y can be used interchangeably in there. There are a bunch of routines. The ones that most commonly going to be utilized are plot XY and plot XZ, and they're plotting the XY and the XZ, or equatorial and meridional cuts of the magnetosphere. And basically what you need to be able to do to use these things is tell it what we want to do for the variable we want to grab, and the plot that you want to make. So the next cell is setting up the plot. And the first 5 lines or so of this cell are just standard stuff to set up the plot that come into play. Setting up a figure, making with a particular size. We tend to use the grid sped object to be able to specify the size of these things. And I'm even though I'm plotting just the one parameter here, the way I'm using subplots to do 2 plots. So I have a plot for the XZ cut that you want to look at, and the color bar that comes into play. And so that's why I've got axis 1 for the plot, and then axis C1 for the color bar object for the second thing there. And then we can return the thing there, do the plot, the visualization of it. And since I haven't actually specified a variable here, it's going to default to plotting up the density. And if you click return on that, or shift return for the Jupyter things, you should end up with an error because I didn't actually define the boundaries first. So you gotta run the boundary cell, then you gotta run the cell for what you want to be able to see for things to come up and plot there. Yes. Yeah. Yep, you're very astute, and you're going to come back and see a little bit later on me using that as a trick to be able to put a plot inside of a plot and to get things going with it. But that's the fundamental idea here, is to be passing around and utilizing the axes objects to get it going on there. Has there Has there been a breakthrough in the Google space? Is it just time that's the answer here, or okay. Okay. Well, so the standard IT solution. Have you tried to reboot the computer? Is the is the answer for the for the access problem? Okay, that's good to know. Thanks for that. All right. So how many folks have been able to make that first plot? All right, we're getting lots of hands going up. We got a few folks that are struggling. Anthony, if you could come over here and help the gentleman in the first row. He seems to be shaking his head for a no, or Adam, and we'll get him going on there. I got Lutz giving me a thumbs up. That's a good sign. So I'm gonna push forward here with the next plot to show a little bit of a repeat of what you saw in the previous cell. In particular, these first 5 lines or so are an exact copy and paste, and just doing the standard same thing to set up the axes objects that come into play. And then I'm calling the routine this time. This time I'm specifying the variable that I want to plot, and in particular, I'm picking Vx. So I'm looking at the x component of the velocity, and since velocity is one of these things that is positive and negative, we want to have a color bar that has a midpoint at 0 for what we're looking at in there. So that's why I'm passing this midpoint equals true object. And then because I've listened to people about how to do color bars, I'm not using Vertis or Magenta for the color bar for the bimodal distribution thing. We're using a red blue. So it's going to be red positive and blue negative. Or I think that's the way it's going to work out. We'll hit the return there to come into play. And we should be able to get for this step a plot of what the velocity profile looks like. And in fact, that's what we get. And I was right. It's going negative for blue and red for positive. At negative 450 is the top there. And so, right around 400 kilometers per second, that's the solar wind flowing in, flowing past. It goes around. And then there's some earthward return flows that are happening in the inner portion of the magnetosphere. How we doing? All right. So I'm going to go for the next one. And the next one is the challenge for everybody there, out in there. And that is to make a plot of the pressure in the inner magnetosphere for this thing. So you got to figure out what the pressure is, and then inner magnetosphere means to me you probably want to change the size of the plot. But why don't we go ahead and have folks do that? And I'll take maybe 2 or 3 minutes here as a pause for that to come into play. If you're curious about pressure, think a little bit about going back, looking at the output that you saw earlier from the variables that are available as a little bit of a hint. All right, so I'm going to pause there. Go to sleep. If you don't specify the color bar, it's just going to take its best guess for the color bar. Multiple successive will drives. Huh? Ah. No worries, no worries. This is the phrase that I always use in computer things of they do exactly what you tell them to do, which is usually not what you want them to do. All right. How many people have been able to make a plot of the pressure? One, two, three. All right, give people a little bit of a chance here. All right. I'm going to push forward just a little bit further here with things for what we're doing going on here, and that is to give what I think is a solution to this thing here. Actually, I need to do one other thing. Let me grab this again. Okay, so I'm gonna go ahead and give what I think is the answer to the plotting question here, and that is that I said make a plot of the pressure in the inner magnetosphere. So the two key elements that come into play here on this are what does inner magnetosphere mean? So I'm assuming the inner magnetosphere is sort of inside of 30 RE. So I'm setting the boundaries for my plotting domain to be plus or minus 30 in X and plus or minus 30 in Y. And then I'm using just copying and pasting using the same setup from before for a box figure that's size there. And then I'm changing the midpoint equals to P and the variable to be P for pressure and the midpoint to be false. And if I was not paranoid, I would try to do a CMAP and specify like magenta or something like that. But I can never remember the name of the various color bars that exist in Matplotlib. So I'm going to just let it pick. Plasma. Okay, let's go for plasma. That sounds like a. So we'll do CMAP equals plasma, all lowercase. All right, so let's see what we get coming out of that, coming into play from that coming into the thing there. So it's reading the pressure, so that variable that exists there. And look at that, we got a plot of pressure in the inner magnetosphere that comes into play here. And one of the things that you can see right away from this is that we in this simulation run here actually have had a plasmasphere turned on. So there's a lot of density in that and pressure in the inner magnetosphere portion of it, making it a little bit harder to see the thing that excuse me the uh the bow shock and whatnot. So let me actually go do one other quick thing here, and let's go look at the documentation for the plot viz routine here. So msphere viz. It's in Camera. Come on, come on. Plot XY. Okay, so this is where you get into trouble because I'm now trying to find my plot XY module to show you guys what it is, and it's not showing up in my documentation. So obviously I broke something in the documentation. So I'm gonna bail out of doing that. I was gonna try and do a little punting with log plots. We'll come back to that in a second. Going into play there. You can plot any of the parameters in X, Y, and XZ in this thing from any step that comes into play for it from there. Yeah. Somebody online. I'm gonna mute folks there. Okay. Got some background noise. I'm sorry, Anthony. What was the question? How did I know the pressure was the P variable? Yeah. So one of the things we have to do in improving on our documentation is doing this. But the list of all the variables that are present in the output file come back and are available to you in the thing itself there. And let's see. Should I try to be clever here? Yes, ma'am. It is there. Okay. All right. Thank you. So KaiPy, Gamera, Gamera package, and then oh, maybe I've got. Okay. So here's the options that come into play for the plot XY thing. For some reason, it isn't filling the full thing out for me. I got to go back and figure out what I did wrong with my documentation there. But you can tell here that this is where it's defaulting to the density being the variable there, and having it use the mins and max that come into play there. And then one option that it does also have is the do log option. So if I come back to this point here and I add do log equals true. I should get a logarithmic version of that. And there you go. You get a bit more ability to see the enhancements that are coming into it from the system there. All right. Anybody not be able to make their own plot of the pressure in the inner magnetosphere? Because if not, we're going to move on to looking at the ionosphere. Yeah, it's weird. It didn't do the log there. Huh. Okay. So bug report. I got to figure out why the do log option is not working in the options there. Okay. So I'm going to move on to talking about the ionospheric parameters that come into play. The process here, grabbing ionospheric thing is getting it pointed to where the files from the output from the mixed portion of it are, and having it go ahead and set up and grab to read the output coming into play. So fairly similar to what we had for the Gamera pipe. You got to do a slightly different setup for the string there. We're going to work on uniformizing these things here that comes into play. And then the next step that comes into play is being able to plot out the ion objects that come into play, and we have it set up for the system to be able to make a fairly sophisticated plot for you of the parameter. And in this case, it's actually defaulting and adding the cross polar cap potential on top of that. But you've got the field aligned current strengths being plotted on that thing there, the mins and maxes for that, and the integrated current power also showing up on this plot to give you a little bit more annotated information. All right, pop quiz for all the students out there. What's the IMF for this time based on what you're seeing in the current pattern? So I heard a by equals zero. Would you care to say why you think it's by equals zero? It's very symmetric. Yes, it's very symmetric. So by equals zero is 100% correct. And it's a pretty expanded polar cap with classic kind of region one sense currents that are showing up there. Maybe if you look faintly, we could probably play with the color table. You can kind of see the edges of the region two currents below that. So it's actually the simulation input conditions at this point in time is just a purely southward 5 nanotesla thing there. So a fairly generic kind of configuration that's coming into play, but something you're able to look at. And then we can look at other parameters that exist and come into play there. And for example, I'm plotting the energy that comes into play for the precipitating electrons, the auroral oval kind of thing there. And so this one is now the next challenge coming to you is to be able to plot the cross polar cap potential. And I have not told you how to find out what the variables are there because I want you to go poke around in the documentation and see if you can figure it out. So make a plot of the cross polar cap potential for the next step in the process. So it's kaipi-docs.readthedocs.io. All right, so I'm gonna show you guys. You could go play around with the documentation. I'm also gonna show you one little thingy that shows up in the uh, uh, Jupyter cells that try to help you with things here. So you can do the ion dot, and then if you hit the dot and you pause for a second, it's going to show you all the functions and routines that are available that are documented in the instance itself. We come down to this dot variables thing, and if I actually just hit dot return there, it's going to give me a print of all the variables that are in the array, the object that's being returned, the class itself. And you can do a standard trick of dot keys from the dictionary object and get the list of where did it go? Right. You can get the list of the various parameters that you might want to look at. And I told you to make a plot of the cross-polar cap potential. So if I do ion dot plot dot potential, theoretically, I should get a plot of the cross-polar cap potential. And in fact, that's what I get coming out of it from that perspective that comes into play there. All right. How we doing? Did most folks be able to get to make their own plot of the ionospheric potential and to take a peek and see what the read the docs structure looks like? All right. The last little piece that I want to get into is this thing that we alluded to a little bit earlier in the discussion with Daniel about the fact that these are axes objects, and the things are using the axes objects to be able to do fairly sophisticated plots that comes into play here. And so we're using this to create an axis that actually has two plots within it, two color bars, two main things that are going to be able to be going into it, and we're adding the tricks to come into play to get you an inset thing that's set up into there. So if I hit return on this guy, you're going to be able to see this plot of the XZ cut of the pressure with the plasma sphere and the bow shock coming into play, and then the inset of the plot of the current with the cross-polar cap potential being input onto it here, and here's this axes object that's being passed in there to get that to work. And then both the color bars are coming out separately here on the bottom, so that you've got the color bar for the pressure and the color bar for the field aligned currents in the plot. You can customize this any way you want. You can do any kind of plots that you want to do with it from there. That the key is to be able to basically be passing around the axes objects that come into play there. And we have these math methods here to generate the color bars and get things to come out with it from there. All right. So what I'm going to do here is kind of stop with my formal portion of the tutorial and let you guys play around. So make a plot of something else. Look at a different parameter. Try doing the insets of those kinds of things. That's the formal portion of what I have. So I'm going to go ahead and stop the recording, and then we can do a little bit more. Come into play.